Everyone, welcome to lecture 3 of week 5 of the course Power Network Analysis, in which we will continue our discussion on evaluation of line parameter evaluation, transmission line parameter evaluation. And this is going to be the second last lecture on the main module 4, which is transmission line parameter evaluation. And in this discussion or today's discussion, we will focus on evaluation of capacitance of actual three-phase transposed lines and how earth or other nearby potentially free or zero potential surfaces can increase or decrease the overall capacitance of transmission lines that we will see. And this discussion will be based on the discussion that we had in the previous lecture, wherein we concluded that if there are n charged conductors of different radiuses r1, r2 till rn, capital N being the number of conductors, and the charges are also different on these conductors, which would essentially mean that the current in the conductors are also different. Then if I take any 2 points, these 2 points we are coinciding them with the centers of conductor number I and conductor number J, then the potential difference between these 2 points, which is Vij, would be the superimposed effect or addition of potentials because of individual charges Q1, Q2, Qi, Qj till Qn, which results in this particular summation term. And the self distances dii and djj are the self radiuses ri and rj, and these distances are with respect to the corresponding nodes between which these distances are evaluated. For example, distance k comma m would represent the distance between center of conductor k and center of conductor m, that would be dkm. So with this, we directly come to the case of capacitance of three-phase transposed lines. We are avoiding all those intermediate discussions on capacitance of actual three-phase untransposed lines. We are directly coming to our main topic, which is we have a three-phase line which is transposed, and transposition is essential, as we discussed in the previous lecture, to sort of bring in an overall balanced effect, because if transposition is not done, because of dissimilar spacing between these three-phase lines, the overall inductance or capacitance would turn out to be unequal for different phases. So no matter whether the system is positively balanced or operating with balanced sources or loads, the network would behave or result into unbalances. So what we have, for sake of our discussion, we have three-phase lines, which are three long parallel strands or conductors. We have still not talked about composite conductors or bundle conductors yet. And these conductors, they are of similar nature, that is, their radiuses are same, r, and the spacing between these conductors, it is varying depending on the transposition cycle in which these particular things are happening. So basically, transposition ensures that every conductor or every phase occupies similar distances as compared to other two phases. So often in a full transpose system, you would find at least 3 equal sections or 3 sections where the distances are more or less similar, so that every phase occupies the same position of other phase conductors. So essentially, if I am marking position 1 and position 2 and 3, then this triangle here essentially indicates the distance between the positions 1 and 2, 2 and 3, and 1 and 3, which is this distance, when conductor A, B, C take up positions 1, 2 and 3 respectively for different transpose cycles. For our discussion, we will for time being consider the effect of earth or ground to be neglected. Field distributions are perfectly smooth. The charges are all residing on the surface of the conductor. Their charge distribution is uniform on the surface. No distortions or no non-idealities exist. And since we are considering our system to be operating in a balanced conditions of a balanced three-phase system, the sum of instantaneous currents have to be 0. So on similar lines, sum of instantaneous charges should also be 0. So QA plus QB plus QC is equal to 0. So now, if we have to find what is the value of capacitance. So as I indicated, we will heavily be relying on this particular potential difference expression. So let's see how this potential difference expression can help in evaluation of capacitance of three-phase lines. So we'll go one by one. What we have here is this expression which is trying to find the potential difference between center of conductor A and center of conductor B when A is occupying position 1, B is occupying position 2. So this 1 here, it should not be confused with the 1 present over here. By 1, 2, 3, I would mean if I were to segregate these transposition halves into 3 different sections. So if this is section number 1, section number 2, section number 3, then 1 here essentially means section number 1, not position number 1. Please keep that in mind. And in section number 1, A is coincidentally occupying position 1, B is at position 2, C is at position 3, and since there are 3 charges QA, QB, QC, which are spaced apart at distances D12, D23 and D31 respectively from each other when the focus is on section 1 transposition. So we can find potentials because of individual charge locations. Essentially, we can make use of the summation expression which we saw in slide number 3 in this particular discussion. So if we use that, let's go step by step. If I have to find the potential between A and B when we are talking about section number 1 because of charge QA, then since QA is the only charge of focus now, so we would have QA by 2 pi epsilon naught. Air is the insulating medium in between these conductors. So epsilon r is perfectly equal to 1 or close to 1. Natural log of some distance ratio. The numerator distance, if you remember, is the distance between the position of charge which is resulting into this potential with respect to the point, the second point where the potential is being measured. So if you look at QA distance with respect to B conductor positioning, which is QB, the distance of concern is D12. So we have D12 as the numerator. The denominator would be the distance between the charge which is resulting into this potential with respect to the first point between which the potential is to be measured. And since QA is coinciding with the conductor itself, and again electric field lines don't exist inside the conductor, they can exist only outside the conductor. So the surface to surface distance with respect to center of the conductor itself is nothing but the radius itself, which is r, and that is how we get our first term, which is shown over here. On similar lines, we have potential difference because of charge QB, charge QC only for section number 1. If we rewrite or extend this for section number 2, which wherein 2 refers to section 2 here, 3 refers to section 3 here, then we have similar expressions. I'm sure these expressions would take time to digest or adjust, but the way I explained the potential difference expression with respect to QA in section number 1, if the same logic is applied, I'm sure you can easily verify or cross-check the other expressions which have been, or other terms which have been explained or written over here in this particular slide. So since I have 3 potential differences for the same 2 points A and B, where A and B themselves are changing their positions with respect to different transposition sections, so we can always approximate these values using the well-known arithmetic mean concept or the average voltage concept. So VAB is the average voltage of the individual potentials that are coming in because of different sections. So if we do that, then VAB expression turns out to be this simple term. So the question here is, what happened to the point or term associated with respect to QC here? Why do we have only terms representing QA and QB, wherein we have brought the notion of GMD here? geometric mean distance, similar to inductance discussion. Why only QA, QB terms are appearing here, whereas in the previous slide there are terms with respect to QC also. Now, if you focus on the terms respect to QC, the first terms being common in all of the three expressions, if we focus on the term QC and try to understand what is actually happening here, QC natural log of D32 by D31 plus natural log of D31 by D21 plus natural log of D21 by D23 is also equal to QC equal to natural log of D32, D31, D21 divided by D31, D21 and D23. D23 is same as D32, so it gets nullified. D31 is same, D21 is same. So essentially we are left with QC of natural log of 1. Natural log or any quantum log of 1 is always equal to 0. That's how this term gets nullified and we have only QA and QB terms. Similarly, if one wants to find VAC, we would have similar terms with respect to QA and QC. QB terms would all get nullified or approximated. Now, why are we trying to find VAB and VAC? Remember, in our previous discussion, we discussed that capacitance, like inductance, when we evaluate inductance, it is with respect to a particular phase. Capacitance, when we are finding, we are starting our discussion with potential difference between 2 points, and these 2 points can be at different potentials with respect to themselves. It's often convenient to evaluate quantities on a per phase basis, where for per phase, the neutral point or the ground point acts as a zero reference or a zero potential reference. So, since we are talking about potential difference between 2 points and we don't know where the neutral point exists, so we are trying to come up with a evaluation or expression where we can find phase A potential with respect to a neutral, and once we do that, once we know VAN, where n is the neutral point, then we can also derive the capacitance of phase A with respect to neutral point, rather than finding capacitance between phase A, phase B or phase A, phase C, because the line-to-line capacitance doesn't make much sense. So, for a balanced system, if we see, we have understood the notion of line-to-line voltages and phase voltages. For a balanced three-phase voltage phasors, VAB, which is the line-to-line voltage across phase A and phase B, choosing VAN, where small n is the neutral point. VAN is the potential of phase A with respect to neutral. As per the definitions of line-to-line and phase voltages, VAB is root 3 times at an angle 30 of VAN. And similarly, VCA is root 3 times of VAN at an angle plus 150 degree, which is also justified or indicated through this particular phasor diagram. If VAN is the reference, VAB and VCA and VBC are also shown. To be specific, if VAN exists in this fashion and if it is a positive sequence voltage, then VBN would exist somewhere over here. If it is balanced, then here we would have VCN. And if we have to find VCA, where VCA is, pardon me, I think it is correct. So, VCA is VCN minus VAN. So, to find VCA, we take the negative of VAN, which would lie over here, VAN, and the addition of VCN with minus VAN would essentially lead to VCA vector, which is also shown over here. So, with that line-to-line and phase-to-phase voltage relationship, we know that this is for sure. And coincidentally, if we add VAB and VCA or VAC, we have VAB plus VAC is equal to 3 times of VAN, where VAN is the phase A voltage with respect to the neutral point. So, essentially, if we add up these two terms, we would get 3 VAN as the effective term. And now, once when we add up, we have two terms. First term is having the same form, QA natural log of GMD by R, and the other terms are QB natural log R by GMD and QC natural log R by GMD. So, let's look at it for a bit. So, we have QB natural log of R by GMD to be added with QC natural log of R by GMD, in which the second terms are common. So this is also equal to QB plus QC natural log of R by GMD. And remember, this is a balanced system. So QA plus QB plus QC is always 0. So it means this is also equal to, sorry, I'm using arrows here, it should be actually equal to, it is equal to minus QA natural log of R by GMD, which is also equal to QA natural log of GMD by R. Minus 1 when taken in as a log, inverses the ratio. So effectively, I would have VAB plus VAC, which is equal to 3VAN, is equal to, I have one QA natural log GMD by R term. I have second term QA natural log of GMD by R. I would also have the third term, which is QA natural log GMD by R. So I have 3 QA by 2 pi epsilon naught natural log of GMD by R, which means VAN is QA by 2 pi epsilon naught natural log of GMD by R. Such a simple, beautiful expression that we are getting. So essentially that is what is mentioned over here in terms of volt per meter, because we are choosing our unit length of the conductor. Once we know VAN, we can use the capacitance expression to find the phase A to neutral capacitance, which is 2 pi epsilon naught divided by natural log of GMD by R. Same is the expression or could be found for other phases with respect to neutral. And this capacitance actually, if we think it from the perspective of network impact, which would be a very detailed discussion in the next module of transmission line performance evaluation. This charged capacitance is also leading to a current known as line charging current, which is the current in the line due to phase to neutral capacitance, because the potential VAN is existing in the transmission line. So no matter whether the line is loaded or unloaded, meaning whether the line is delivering any load or not, irrespective of the load, this current would always exist in the transmission line, because the line is charged, it is activated, is just carrying some potential. So because of this capacitance, whose expression is given over here, JXACAN, where so XCAN is 1 by J omega CAN, where omega is 2 pi F. So if I have to find the charging current IA, it is X is just 1 by omega CAN. So if I have to find charging current, so VAN divided by minus of J X CAN, which when I substitute it over here results in this particular term. So this is a line charging current which is flowing even when the load current is 0. That means the line is not delivering any actual load. And it results into a very interesting effect known as Ferranti effect, wherein due to light load conditions, the receiving end voltage tends to be higher than the sending end voltage. It would sound pretty awkward that how come the load voltage tends to be more than the source voltage, because it is the source voltage or the source energy which is transferring to the load. So how come load voltage can go up? The basic reason why that goes up is because of this charging current, because this serves as a source of additional reactive power for the system, which leads to increase in voltage at the receiving end. We will discuss these aspects in length when we discuss the next module. The effect of bundling or effect of composite conductors is going to be exactly the same. Instead of actual R, you can get the expressions in terms of GMR, which is geometric mean radius. Remember, geometric mean radius in capacitance is the actual radius or the actual overall radius, not the skin effect based radius which we saw in inductance. Please don't get perturbed. We'll again have one more discussion, which is going to the next discussion, wherein we will see numeric examples of how these evaluations can happen. And as I mentioned, the log term in the capacitance, it would have GMR instead of actual R, when GMR is calculated based on actual radius, not the R dash, which is used in inductance evaluation commonly for bundled conductors or composite conductors. So with that, we conclude our discussion of capacitance of three-phase lines. We have one more interesting aspect, which is what is the role of earth or any other potentially charged free surface on line capacitance. Since our transmission lines, they are overhead lines, and the earth is always at the bottom of these transmission lines and towers, so there is a concept known as right of way. So earth has a role on capacitance, and it influences transmission tower design. So why is that? It is because, as I mentioned, earth influences the value of capacitance. So how that influence comes in is what we would understand, and then we will see what corresponding actions are there in place to minimize the effect of earth. So there can be two effects to start with. Either the effect of earth increases the overall capacitance or decreases the role of capacitance. If the earth role were to decrease the value of capacitance, then probably it would have been a beneficial effect, because in that sense the charging current would also have been lower and other consequences could have also resulted in. But the reason why we are discussing this would have become obvious by now, that the effect of earth, it leads to increase in line capacitance. So how is that happening? Let's see that. Earth acts as an infinite source of sink or source of charges. It can be treated as an equipotential surface with zero potential. And if we have an overhead line which is carrying current or is charged, assuming it to be positive charge, then the electric field lines, as I mentioned, I forgot to mention that electric field lines always originate from positive surfaces and terminate at the negative surfaces. So since earth acts as a sink or source of charges, it's always neutrally potential or at zero potential. So for a positively charged body plus Q, the arrows or the lines which you see here are the directions of the electric field lines. These electric field lines would originate from surface of conductor in an orthogonal fashion, and they would terminate at the earth surface again in an orthogonal fashion, because electric field lines with respect to corresponding charged surfaces, they always have to be orthogonal. So electric field lines, they are originating from conductor which are orthogonal, but they are not radial anymore because the distortion has happened, the earth effect is now coming in, and field lines are also orthogonal to the surface of the earth. So how do we encounter this effect of field lines coming in from the charged body to the earth? Because if the field lines can exist, then we can also mark corresponding orthogonal surfaces which would turn out to be equipotential surfaces, and the equipotential surface 0 is appearing over here. So at a distance above, a little above over here, the potential difference might be higher and higher till the line whose operating voltage could be of few hundreds of kVs, or let's say 220 kV or 400 kV. Such operating voltages are the usual transmission line voltages, 765 kV. These are line-to-line voltages. Phase voltages could also automatically be obtained. If the electric field lines originate from the charged body and terminate at the earth, and earth is at zero potential, so as I move higher and higher, the potential would increase and eventually it would become equal to the line potential. So if potential exists, that means capacitance will definitely exist, because C is inversely proportional to V, or it is equal to Q by B. Q is existing, V is existing, so definitely in between this surface which is occupied by the air, C value should definitely exist. So that's the reason how earth influences the capacitance value. So how do we do that? Kelvin came up with a very beautiful idea. He suggested that if earth acts as a zero potential plane or a ground, that means we can denote a negative charge of same quantum as the positive charge Q to be present at an equal distance below the surface of earth, h being the distance between the charge plus Q from surface of earth. And if zero potential exists, that means this particular surface, which is a zero potential surface, is orthogonal to the electric field lines which are originating from plus Q and just terminating at the surface. I am increasing the arrows so that these can appear to be originating from plus Q, the values of E, and terminating at negative Q, again in an orthogonal surface perspective. And if zero potential exists, that means if this is at plus V, I can also associate a corresponding minus V at a depth h from the surface of the earth, and that's how the consideration of effect can be taken care of. So Kelvin suggested the method of charges or images. Basically, they are image charges. This negative Q does not exist. It is a fictitious or an image charge which is being considered to account the factor of presence of earth potential or zero potential. So field lines, they are orthogonal to earth, zero potential surface thus can be removed while considering the evaluation of capacitance due to earth. So what we have here is we have the most complicated case. We have our three-phase transposed lines which are transposed at different sections. Remember 1, 2, 3, they can be different from the section marking. So this can be section 1, this can be section 2, this can be section 3. And conductor A, B and C, they are taking different positions 1, 2, 3 over here. These 1, 2, 3 distances are also present and the same distance arrangement is shown over through this particular triangle D12, D31, D23, and these charged surfaces or conductors are at distances H1, H2, H3 from surface of earth. Their in between distances are D12, D23 and D31. Since we have to consider the effect of ground or earth, we are assuming image charges or negative charges of negative quantum of charge and at a distance of minus, let's say, okay, so this has particularly not been shown over here. So if this is h1 by 2, then this distance is also h1 by 2. This distance is h2 by 2. The image of charges say this is h2 by 2 in half. And similarly, if this is h3 by 2, then the image charge here is also at h3 by 2. Similar inference could also be made for other distances correspondingly. I'm not going into details of that. But given this tower arrangement, given the heights of these conductors from the respect of earth, the other distances h31, h12, they can all be obtained and evaluated. So we have three-phase lines of same radius. Their charges are QA, QB, QC. It's a positive balanced system. So at any point of time, the sum of charges is 0. Image charges have the same charge but negative quantum. Field lines are all orthogonal. Surface charge density is uniform. There are no distortion effects. So we now go into finding capacitance because of effect of earth for a three-phase transposed line. And we use the same notion of finding the potential with respect to different points. So what we have here is we trying to find the potential between conductor A center and conductor B center when A and B are at section 1. So let's spend some time here. So if we talk about section 1 position and we want to find VAB when AB are in section 1 with respect to charge QA, then this would be equal to QA by 2 pi epsilon naught natural log of the first distance on numerator would be distance between QA and B. In this case, QA is over here, QB is over here, so distance is D12, which is this distance, and divided by the radius of the charge because QA with respect to the other conductor A is the self radius, so we have plus R. Similarly, we would also have VAB with respect to minus QA when A and B are in section 1. So our expression becomes minus QA by 2 pi epsilon naught with natural log. The first numerator should be distance between minus QA and B. If we look at minus QA, it is sitting over here. B is at position over here. The distance is h12. So natural log of h12 divided by distance between minus QA and A, which is the distance between these 2 points, which is h1. If we add these two effects, let's say VAB overall 1, then this is nothing but QA 2 pi epsilon naught natural log of D12 by R minus natural log of H12 by H1, which can be again simplified as 2 pi epsilon naught natural log D12 H1 by R H12. So this is the first term only because of charges QA and minus QA, which also is appearing over here. And that is how the first term is obtained. Similar terms can be obtained for QB, QC, and then you can also find the potentials with respect to other sections 2 and 3. And if we Take their average, we get VAB as this particular expression over here. We can also find VAC, trying to find VAN actually. So VAN is VAB plus VAC by 3. So, and also QB plus QC is minus QA. So we get VAN as this particular term, wherein if we now find capacitance, then we have this term over here. Remember, when the effect of earth was not considered, this term was not present at all. Okay. Now, with consideration of earth, we have this additional term, and let's focus on this term for a moment. Let's not worry about the negative sign. Let's talk about this ratio for a moment. What do you think? The ratio or H12, H23, H31 by H1, H2, H3, is it going to be less than 1 or is it going to be more than 1? It appears that no matter how the tower arrangement is, H31, H23 and H12, their product is obviously, or individually if we compare, these distances are respectively more than H1, H2, H3. It may not be individual comparison, but definitely these distances are larger than the self distances. So the ratio inside the log term here is a term which is more than 1. That means natural log of this term is going to be a positive number, which means when I multiply with minus 1 by 3, this term overall is trying to bring down the denominator value. If denominator goes up in a particular ratio, the corresponding capacitance value should accordingly go up. And that's the reason why the ratio being positive, overall capacitance due to earth increases. What is the alternative? How can we minimize this increase in capacitance? If this ratio tends to be equal to 1, so natural log of 1 will become 0. When this term can become 1, try to design your transmission towers or place conductors which are having high right of way from the surface of earth. So as distance between conductor and earth increases, these products, they become more or less equal, and that's where the concept of ROW, or also known as right of way, comes in. Higher the potential of a transmission line, higher is its ROW, lower the potential of the line is, the ROW can go down, so that the capacitance effect of due to earth is minimized or neglected. So additional term, when this ratio becomes close to 1, additional term would tend to 0, and hence the effect of earth on capacitance becomes negligible. That's all for today's discussion. As I promised, as I discussed, I'll take up numeric examples and also try to understand how manufacturers' data can be used, because GMR and GMDs, they can be very well obtained from manufacturer data. So we'll take up examples, numeric discussions of how GMR, GMD can be evaluated for line capacitance, line inductance evaluation in the next discussion. Thank you.